Okay, so let us now continue and let me finally put down, since we did define all the notation, put down the definition of reducible and irreducible. For the next one or two lectures, we will also be using a slightly abstract notation, and so we say that a representation is a map after all, T, which is a map from G, group G to GL acting on some vector space H, is called reducible if there exist subspaces U and W of H, i.e. H can be written as direct sum of U and W, and both U and W are separately invariant under actions of T of G. So invariant means that that subspace never gets mapped into T of G acting on the subspace U will never map anything of U into W and vice versa. So if this happens, then the representation, this particular representation given by this map T is said to be reducible. And if there is no such space, if no such subspaces exist, it is called a reducible representation, irreducible representation, and irreducible. The other definition is of faithful and unfaithful, so we can here highlight. A representation T in which T of G is unique for every G, is called faithful. But if Tg1 equal to Tg2 for G not equal to G1 not equal to G2, then it is unfaithful. and we already saw the example first. The worst kind of unfaithfulness is where everything is represented by just 1. Nevertheless, that severely unfaithful representation is irreducible, because you cannot reduce 1 to anything else. Okay. So it is an irrep, and as we will see, it very importantly anchors the whole calculation of Schur, the whole calculation of the great orthogonality theorem. Okay. So the only next thing I want to remind you is that we also checked last time that you can always make any representation unitary. So all these matrix representations are unitary. Can be chosen to be unitary. So in other words, the matrices D are unitary. Then, sorry, you have any comment to make? Do you have any comment to make? So if you have, then you please tell the, it may be useful to the whole class. So. And here there is a terminology that if there are representations called adjoint, if so D, the representation D star is called the conjugate representation. So note that if D alpha of G, so this set is a rep, it can be reducible also, that does not matter. If D alpha G is a rep, then the matrix is D alpha star of G is also a representation, and it may not be transformable into D under similarity transformation. So they are inequivalent. So I should say in general, inequivalent, in that it cannot be brought to D by a similarity transformation. And it is called conjugate representation. This we are not going to need in near future, but it is worth keeping in mind. To the one with D. And there is another one where we take D transpose inverse. Similarly, transpose and then inverse. Constitute another inequivalent. I have written constitutes because now I am referring to the whole set. So there is one entity. So this set constitutes another inequivalent representation which is okay, another inequivalent representation, and it is called the adjoint representation. It is called adjoint 2. I have to, the word adjoint is used in a different context as well, but that's why I am saying adjoint 2. We will see that so there are some accidental cases. For very small groups, it turns out that sometimes the two can actually be put in. So that's why I said in general it is inequivalent, okay. But there are some special cases where they coincide or they are equivalent under a similarity transformation. The classic example is the group of SU2, the spin group generated by Pauli matrices. Turns out that Pauli matrices can be complex conjugated by similarity, their own transformations you can form their complex conjugates. So, but aside from those special cases you don't have, and I just said it without too much detail. We will come to it in the second half of the course, okay, where we go to continuous groups. Now let us prove the so-called Schur's lemma. Oops, I am again running out of time, and I don't like to present detailed argument when we are short of time. Let us see if we can. So let me state Schur's lemma in the formal sense. I am probably mentioning Schur's lemma the 4th time, but it is important enough that one can say it several times. Suppose we have one representation T, which is from the group G to GL acting on some vector space V, and a T prime which is from group G into the general linear transformations on another vector space V prime, and also a map A which is from V to V prime, which is a linear map. Or a linear operator. So these are the n by or m by n matrices that convert an size n space into a size m space. Now if it happens that if the condition that ATG equal to T prime G on A is satisfied for all G, then there are only two options. A is an isomorphism or A is 0. And let me add here, in which case V and V prime are isomorphic, are essentially the same. Or A is 0, the matrix A is 0. Okay. This particular lemma, which in some sense even looks a little too simple, it does not seem to say anything very profound, turns out to be key to proving the great orthogonality theorem. And the way one proves it, to prove it, and so we will only set up the beginning of the proof and we will go to the proof next time. So to prove this, we need to introduce a concept called kernel of a map, and this proof I am taking from the book by Hassani. I will upload the chapter from Hassani's book. I didn't find proofs in many places, and Hammermesh I find difficult to read anyway. So to prove this, introduce the idea of a kernel, not kernel, the idea of kernel of a linear operator. Kernel of a linear operator is all the elements that it maps into a zero vector. So given A, taking V to V prime, let us say, then ker A is essentially a subset of V such that A of all A, let me write quantum mechanics notation, equal to 0, where A belongs to V. Now an important property of this kernel of linear transformations is that it is one to one. So a linear transformation is one to one only if its kernel is 0. In fact, it is if and only if its kernel is 0. So the only if part is clear, which means that if it is a one-to-one transformation, then clearly its kernel has to be 0, right? So part 1 there is only one element, V is mapped into zero, and that element must itself be 0. Zero belonging to V. This is due to linearity of the transformation. Part 2 is the opposite, which is that if it is mapping if the kernel is 0 vector, then it has to be 1 to 1. So, suppose it maps two different vectors into 0 vector. Suppose it happens that A of vector A1 is equal to A of vector A2. So, here we are saying it is not 1 to 1. So, suppose i.e. not 1 to 1. But then, because we are using a linear transformation, it means that A of A1 minus A2 vector is obviously equal to 0, because I take this to this side and I use linearity of the operation, right. So, linearity is very important in all this. But then A1 has to be equal to A2, because the kernel is 0. Ker A is 0 vector, i.e. A1 minus A2 is the 0 vector, i.e. in usual language A1 is equal to A2. The difference between two vectors is the 0 vector, then the two vectors have to be same. So, the proposal that two distinct vectors are taken into 0, two distinct vectors have same image is not possible. I like to write it in English. Thus, the hypothesis of two different A1 and A2 having same image is contradictory. So, if the kernel is 0, then the map has to be 1 to 1. Okay. So, this we will use in an important way in proving Schur's lemma next time, that the kernel of a transformation is 1 to 1 or injective if and only if its kernel is 0.